We are going to, you need your journal, you need these pieces of paper, and we're going to set up our plate tectonics unit. So we need to open to our next available page, and mine is after all of the Newton's laws of motion. Okay, so Newton's laws of motion. So on the top of your next available page, we are going to write Newton's laws of motion, and that's where we're going to tape in the lab sheet when you get it back. So Newton's laws of motion will go on the lab sheet. We'll go there, sorry. So then on your next available page, you're going to write conclusion. So the conclusion will go there, and this will be, I'm just going to put motion test, and this will be where the multiple choice test goes. So therefore, when you get those three things back, you'll have a spot dedicated already for them to be taped into your journal. Okay, so now, your next available page, after you have those titles written down, we're going to find this diagram. And we're going to tape this diagram onto your next available page. And we're going to be labeling some things on this page. But we're going to get it taped in, so let's tape that in. Doesn't take really big pieces of tape, just 4 little small pieces, one for each corner. Doesn't take really large pieces, so there's that one. And we're going to label it Plate Tectonics title page. Okay, so that's your Plate Tectonics title page, and of course don't forget the date. And I'm making this recording on the 24th, so I'm just going to put the 24th up here. So there's the title page. The next page is going to be our teaks. And also don't forget to put the date up there. Okay, and so the teaks look like this. It says forces that change Earth. And so that's going to go on your next page, and it will fit sideways, barely, but it fits. So once again, just 4 little pieces of tape. It doesn't have to be real big pieces. So 4 little pieces of tape. There we go. And that is on there. So you've got your title page, you've got your teaks. So both those are on there. As you tell, somebody didn't get their pages all numbered in their journal. Okay, so then our next page, you have 2 pages of vocabulary. Alright, so 2 pages of vocabulary. I'm going to take the one that doesn't have the title on it, and I'm going to put it towards the bottom of the page. And I'm going to tape it down. Once again, just small little pieces of tape, all you need. So tape that down. So there's my bottom layer. And then I'm going to take the one that has the title on it, and it will go on top. And since it has a title, you don't have to write it again. So then that one will go on there. And I'm going to tape it across the top, make a flap. And then of course don't forget the date up there. Okay, so you should have an orange tab, and on the orange tab you're going to write Plate Tectonics. So we're going to write Plate Tectonics on both sides. like my tab where when I open it up, I'm actually on it and not having to turn another page. So I am going to put it on this page that has the teaks because of how my journal is looking. Push that out. So I have that tab. I'm going to tape it down on that side, and then I'm going to tape it on the vocabulary side, and then my tab is in. Alright, so then I want you to either take a highlighter, colored pen, or something that you have, and you're going to go in on your vocabulary, and I'm going to highlight the title. Right, and I know they're bold and I know they're underlined, but go in and highlight the words. That makes them stand out better, easier to read. So just real quickly, either draw a line under them or highlight them. Okay, so I have them highlighted. That's done. Matches my tab. Okay, so I'm going to highlight the forces that change Earth here. This is what the state of Texas says that you need to know. You need to understand the historical development and evidence that supports the theory of plate tectonics. You need to understand how plate tectonics relates to the formation of different crustal features such as mountain ranges, trenches, subduction areas, volcanoes, island arcs, and you're going to be able to look at topographic maps and interpret them. So those are the things the state of Texas says that you will know at the end of this unit. Alright, so to this picture here. Okay, first thing that we're going to add to it are convection currents, because right now we know that is because of convection currents in the mantle that's causing these lithospheric plates to move, because they ride on top of the asthenosphere, which is the upper part of the mantle, and as those convection currents come up, they act as wheels and pull and drag those lithospheric plates around. So we're going to draw convection currents. So we have the inner core, which is solid. Okay, and we have the outer core, which is liquid. And it is liquid nickel and iron. The inner core should be a liquid also, because it's actually at a hotter temperature or higher temperature than the outer core, but the pressure is so intense that it doesn't allow it to be a liquid, and so it is a solid. And so there are convection currents in the outer core also, and the convection currents in the outer core cause the inner core to spin, and that actually gives Earth's magnetic field, which helps protect us from different types of solar radiation. It's very important. Okay, but we're going to talk about these convection currents that'll be out here. And so we know that this is hot, and so the rock is going to heat up, and as it heats up, it's going to become less dense. So this will be less dense. So it becomes less dense when it heats up. Okay, the molecules are going to be spreading farther apart. When it gets farther away from the core, it begins to cool down because it doesn't have that heat source anymore. So as it cools down, it becomes more dense and it's going to sink. Okay, so this will be more dense. So this sinking rock that's more dense is going to push this less dense rock up, and what you end up with are these circular motions, which is called a convection current. And as these convection currents turn, it pushes and pulls the plates on Earth's surface, just drags them along. Now they only move up to maybe 10 centimeters a year. We're not talking about a big movement, but over time that builds up. So these are called convection currents. So draw a line out, and this is called a convection current. So when you are doing your history, it talks about Alfred Wegener, who came up with really great evidence to prove that at one time all the plates were together, and he called that supercontinent Pangaea. He looked at the fossil evidence and talked about how the fossils could not be as widespread on all these different continents if they hadn't been put together. He looked at the climate in Antarctica. They found coal deposits. They have found fossil remains of tropical plants, and so they know that this area had to be closer to the equator where it was a lot warmer. He looked at the landforms that make up the edges of continents and saw how, because the rock lays in layers, and we call that the strata, and so how that matches up perfectly, and know that they had to be together and the rock had to be laid down at the same time in order for them to match up, to have the same fossils in there, to have the same types of rock. But what he could not prove was that mechanism that caused the plates to move. And without that piece of evidence, the scientific community as a whole did not accept his hypothesis. And so his hypothesis of continental drift was not accepted at that point in time. But there were people that listened to what he said and said, yes, this makes sense to us. What is that mechanism? And so then along came Arthur Holmes, and Arthur Holmes was a physicist, and he studied how heat is transferred, and one of the ways that heat is transferred is through a convection current. And this is a convection current. This is how our weather works. This is how your AC works in your house, okay? That it moves as a convection current. And in this particular type of heat transfer, the medium, the material that it travels through actually moves with it, okay? And so he said this could be what's going on, that there are convection currents in the mantle, and that's what's causing the plates to move around. And then during World War II, we were using sonar, and on one of the ships was Harry Hess. And Harry Hess was a geologist, and they really thought the ocean floor was just this flat basin. That's what they really thought. And so once they started using the sonar, they started finding mountains and volcanoes and trenches and all kinds of different things under the ocean floor. And he was able to use that information to develop his seafloor spreading. And of course, seafloor spreading just says that as the two plates are dividing, as you know, that divergent plate boundary, as they're dividing, the molten magma comes up through. And so, and as they move across the side, eventually that continental and the oceanic plate are going to meet up, and then you're going to have subduction. And so he came up with seafloor spreading. And then it just keeps going with J. Tuzo Wilson, who said, well, the Earth's plates, or the Earth's crust, is broken up into plates. So he named the seven, or it's more than seven, the basic plates, and then eventually, and there's other scientists involved. They all found these little bits and pieces, and then Dan McKenzie in the 60s put all those pieces together and named it the theory of plate tectonics. So the theory of plate tectonics is actually one of our newer theories within science. And so it did take a long time because Wegener proposed this in the early 1900s. And so it took quite a while before it actually went from his hypothesis. We started finding the proof to prove his hypothesis to now the theory of plate tectonics. And so it's just understood that it is these convection currents in Earth's mantle that's moving the lithospheric crust. And the lithosphere, that's the part of the crust we exist on, this very, very top part up here. Okay, so we're going to take this and we're just going to color it a little bit. So I'm just going to kind of give it a few little colors. So I'm just going to color this molten area a brown color. Okay, and so remember that in The outer core, there are actually convection currents in the outer core also, and they control the movement of the inner core. So we have that. Okay, and so this is liquid, iron and nickel. You can't see what I'm doing. And so we're just going to kind of give it a little bit of a layer right here. This is just that dividing area between these two. And the mantle, I think since it's really hot, I'm going to give it a red color. And we can put some more convection currents in here. So let's say this one is moving this direction. Okay, so we have our convection currents, and I'm going to just make this red because it's a really hot molten layer. There we go. We've got that colored. So I keep shrink this a little bit. So we have our inner core, our outer core. This is the mantle, and the mantle actually goes up. The asthenosphere and the lithosphere are part of the upper parts of the mantle. The asthenosphere, it is a liquid layer of rock. So your asthenosphere is your liquid layer of rock. Okay, that's what asthenosphere means. And then the lithosphere is those harder plates. That's what we are on, of course. And the lithosphere is made up of both continental and oceanic crust. Okay, and that's all you have to do for your title page, and it is done.